Okay, so we've defined this concept of definability of a set. We say that a set is definable if there is a formula which defines it, right? So uh, that's kind of where we're at. And what we're interested in doing in this video is kind of structuring a hierarchy of definable sets. And we're going to notice, and this is kind of where things are going to start to fall into place, I think. This is where the clicking sounds are going to start to happen. But before we can get to that, we do need to do a couple preliminary things. So first of all, I have to define what it means for two formulas to be equivalent, which is a word I've said a ton of times already throughout these videos, but and that was in the metamathematics. At that point, I'm talking about logical equivalence. Logical equivalence means that A implies B and B implies A. If I say if and only if, that's also what I mean by that, by the way. But what does it mean for two formulas to be equivalent, kind of in this, like, with it, how am I defining it for the kind of math, the toy math that we're talking about? And the way that I'm going to say that is simply that they define the same set. So two formulas are equivalent if the sets that they define are the same. Now, this is a definition of equivalence that really only applies to formulas with free variables, but that's all I care about right now. And this does correspond to logical equivalence in the actual meta-mathematical sense. So two formulas are equivalent if they define the same set. And so let's just kind of move with that. So two preliminary facts that we need about quantifiers. So here's just some facts about kind of logic within the like inside of the mathematics that we're talking about in the meta-mathematics. So first of all, there is no such thing as finite quantification. Finite quantification is fake. And so and the reason for that is if I want to say something like there exists an x less than or equal to 5 such that phi of x, I could just as easily have written just 5 or signs, right? I could have just said phi of 0 or phi of 1 or phi of 2 or blah 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 up to or phi of 5. Same thing with and, right? If I have for all x less than or equal to 5, I have something that's true. I could have just as easily said phi of 0 and phi of 1 and ... up to phi of 5, right? So to put these finite quantifiers here is fine, but it's not a real quantifier. You're just doing it shorthand for something that you could have written out without a quantifier at all. So there's nothing that requires finite quantification. So we don't have to really consider it in our hierarchy. 2 is that quantifiers can always kind of be pulled out to the front. So here's an example I gave here is that the way I've been doing this before, like pretty much everything I've ever written so far involving quantifiers has been like this. Right, if you look here, the only exception's been this one, actually. But usually I write stuff like this, where I say I put all the quantifiers in the front and then I put stuff after that. But you can, and so what I'm trying to say here is that you can always do that. And this definition of the composites is actually a perfect example of this. I think that it's more descriptive and understandable to put the there exists a z here, but there's no real reason to. I could pull it right out. It doesn't really matter. I could just write this as, there exists a y and there exists a z such that, and then write the same stuff. But I guess I'll write it out. Such that y is not equal to 1, I'll just write it like that, and y is not equal to x, and y times z equals x. Oops. And so these are obviously equivalent, right? You can see immediately that these are equivalent. I could just pull quantifiers out usually. And there's another thing I should say about quantifiers too. This is a little more technical, and I hope I don't screw it up trying to explain it. This is something that I've probably been a little too flippant about. Is that I also have never done something like this, where I put a there exists and then another there exists. Usually I'm alternating back and forth. There exists x for all y exists z ... This is also something you can always do. You never need to have there exists a y and there exists a z. You could just write there exists a single xz. I could write there, for us I think I'll just write there exists a pair xz and then write the stuff. You only really need one there exists quantifier. If I have a for all in the middle here, then that kind of follows afterwards. It has to follow afterwards. You can't pull this, you can't like merge this exists and for all. You're saying there exists an x which applies to all of the y. But if you have a there exists followed by another there exists, then you can just kind of merge the two together. Now, obviously, we've never quantified over stuff like this before, and that's you don't need to do that either. You could talk about like what I've been trying to avoid talking about for a while now has been like coding and decoding functions. And this is getting a little far afield, but I could write one number here, and then I could have like a decoding system which allows me to kind of decode two numbers out of that number in such a way that you get everything. And so I could just kind of say there exists a single number and then talk about the decoding of that number and then get two numbers out of that single number. So at that point, I'm still just using there exists in the way that I've used it before, and I've collapsed it to a single one. But if none of that made sense, just think about it like this. So those are three important things to note about quantifiers. I can always pull them out to the front, that finite quantification does not exist, and that I never need to kind of repeat the same kind of quantifier twice. In other words, let me summarize it over here. In other words, any formula phi is always equivalent, can always be thought of as equivalent to basically this. I could say like phi, and typically when you write equivalence, you do like three lines like this. I could just say there exists, an x1 for all x2 ... up to like, something. Maybe another one there exists, xk, such that some psi of x1 ... xk. I can always kind of think of it in this kind of standardized form in which all the quantifiers are out front and they're alternating, and then I have some other thing that's true about them after that. This is called the prenex normal form, actually. Prenex normal form. You can always kind of standardize any formula in terms of the sets that they define, or just logical equivalence in general, in this way. And so that will be important to note for the hierarchy I'm about to define, because with all of these things known, it will be obvious that the hierarchy I'm defining is the hierarchy of every definable set. So let's now define that hierarchy, which will be a hierarchy of every definable set. Okay, so here we are. This is a really important moment for us. We're finally ready to define a thing that we've totally, actually never mentioned before, the arithmetic hierarchy. You've heard this before? No, you didn't. No, you've never heard this before. We've never defined this. So let's define something called the arithmetic hierarchy that you've definitely never heard before. So we're going to call a well-formed formula delta 0. This is a capital delta, if it is equivalent to a formula which has no quantification at all. So in other words, so that includes finite quantification too, by the way. So delta 0 is either no quantification or finite quantification, but finite quantification we said is fake, right? So delta 0 formulas, no quantification. That's all it is. So we're not defining the set yet. We're not defining the hierarchy yet. What we're defining now is a way to classify formulas. A formula, again, is sigma 1 if it's equivalent to one of the form there exists an x such that phi, where phi is a delta 0 formula, right? So sigma 1, there's a lot of text here, so I kind of feel like isolating this just to make it very clear. Sigma 1, if you're basically of the form like there exists an x such that phi of x, right? That's the form for that's a sigma 1 formula. A pi 1 formula is going to look like for all x phi, where phi is delta 0. And so this is, by the way, delta 0. In other words, quantifierness. Quantifier free. Pi 1 if for all x phi of x. So same thing, right? This is delta 0. So basically you're building sigma 1 and pi 1 kind of out of the delta classes, the class before that, the level before, underneath that. And then finally we're going to let delta 1 be the intersection of, well, I shouldn't have written it like this, actually. I can't really define it that way because these aren't sets. This is just a formula. So, so I should have said, and a formula is delta 1 if if it's equivalent to both, if equivalent to both a pi 1 and a sigma 1 formula. So if you can write it either way, then it's a delta 1 formula. And so what we're gonna do is we're just gonna kind of keep going like this. So it's sigma 2 if there's two quantifiers, right? And the leading one is a there exists, and it's pi 2 if there's two quantifiers and the leading one is a for all. So it's just kind of like, if we wrote up here, we mentioned up here that you could always do it in this way. You could always where's what I wrote? Oh, I wrote that on a different page. So yeah, we mentioned that you could so we mentioned that you could do this in this quantifier. We mentioned this like pre-next normal form. This way that you could always write it down. You could always write every formula down with these like leading alternating quantifiers like this. And so we're just kind of making a hierarchy in the obvious way using that. So sigma 2, means you have two quantifiers and the leading one is a there exists. Pi 2 is that you have two quantifiers and the leading one is a for all. And then at the bottom, you always have a delta 0 formula, that is to say a formula without any quantifiers. And then more generally, it's going to be sigma k. A formula is sigma k if it's equivalent to one of the form there exists x1 such that for all x2 there exists an x3 ... up to like xk, right? K is the number of quantifiers. Phi, where q, I had to write q here instead of there exists or for all, because it's going to be different depending on whether k is odd or even. So if k is odd, if you have k many quantifiers and you're alternating like this, then this has to be a there exists. And if k is even, then if you start with a there exists, then this has to be a for all. So that's kind of annoying to think of it like that way, but you can just replace this with whichever one is your favorite and just not really worry about it. I like to have there exists as like a bookend. If I'm going to have one here, might as well have one here. So let's just make it look like this. Just k many alternations starting with a there exists quantifier. That's what it means to be sigma k as a formula. This is getting pretty technical, right? And I'm hoping this is still approachable to everybody. I think it is, but it's definitely going to be getting close to being a challenge. But don't worry, this probably is the most challenging part. If you can process this stuff, then we really are home free for the rest of it. And we're not far off from being past this part. But it's super important. We have to talk about this. So if phi is sigma k, okay, so basically that defines the entire hierarchy. And I want to basically make it clear why this is a hierarchy. So if phi is sigma k, then it's also going to be sigma k plus 1, pi k plus 1, delta k plus 1, sigma k plus 2, pi k plus 2, and so forth, right? And the reason for that is that I can always just kind of tack on another pointless quantifier if I need to, right? K, remember, k is the number of quantifiers. So if I have a formula that's equivalent to a formula that only requires k quantifiers, then it's still going to be, I can just put on another quantifier and I still have something equivalent. Right? If I say like, if I say that x is less than y, right, this is a delta 0 formula. But if I just tack on a there exists a z such that, well, then I have something equivalent because z doesn't matter at all. And so this now has become a sigma 1 formula. And if I want a pi 2 formula, then I could put for all w, and I still have something equivalent. I could just tack on useless quantifiers to make new equivalent statements. So it is a hierarchy, just even in the sense of these formulas. If I have a sigma k formula, then I have a formula that is everything above that. Everything above that. And so finally, we're ready to find the sets themselves, or the classes of sets. So we're going to say that a set is in the class delta 0 if it is definable by a delta 0 formula. Simple enough. And we're going to say that it's in the class sigma k if it's definable by a sigma k formula, and so forth. We're just going to say that, we've defined this hierarchy of formulas, and each formula defines a set, so we've also defined a hierarchy of sets just by virtue of that. So a set is in the class sigma k if it's definable by a sigma k formula, and so forth. And so this produces a hierarchy of all definable sets, because remember we said that all formulas could be kind of equivalent to a formula in this form, in the sense that they define the same set. So we get this hierarchy of definable sets. We have delta 0 at the very bottom, and delta 0 is a subset of delta 1. That's what these arrows mean. If you're kind of going in these directions, this means subset of. So everything in here is also in here. Every definable set that is a delta 0 set is also a delta 1 set, and so forth, because you can always tack on those useless quantifiers. And so, yeah, you have delta 0, then delta 1, and this picture probably looks very familiar. We've drawn this before already. Except when we drew it before, yes, you got delta 1, and delta 1 is contained inside of these two, and it's pretty clear, you know, by the way, I said that your delta 1, where did I write this? Delta 1, if you're equivalent to both a pi 1 and a sigma 1 formula. But if you're equivalent to both a pi 1 and sigma 1 formula, then you're an S1 set. You're a set that's in this class delta 1, if and only if you're in both sigma 1 as a class and pi 1 as a class, meaning that you're in the intersection of the two. So I probably should have written that somewhere, right? Delta k, oops. This thing is here. This thing is defined by being the intersection of these two sets. This is sigma 2 intersect pi 2, and then this here is like sigma 3 intersect pi 3, and so forth, right? And so this is the hierarchy. This is what I'm going to call the arithmetic hierarchy. My computer is freezing. So this produces a hierarchy of all definable sets, and we call it, because we're talking about arithmetic, remember we're talking about the natural numbers, we call it the arithmetic hierarchy. Now, as you know, I've been lying to you. We have defined the arithmetic hierarchy already, except it didn't make sense to call it the arithmetic hierarchy when we defined it originally. We've redefined it in terms of this concept of definability, but we've already defined it in part 2, at the end of part 2. I think that was the end. Yeah, I think that was like the last thing we did, in terms of computability. And so in the next video, we're going to compare those two definitions, and we're going to show that they are the same. And that will be a very important moment for us.